Let me. So in the previous session, we are discussing uh, about the new algebraic structure, which is called the Boolean algebra, and I told you that there are certain properties which needs to be followed by the elements of the non-empty set considered, and the properties which I defined in my last lecture was actually known as the Huntington's postulate. On the basis of this postulate, we call the structure as Boolean algebra. And I was showing you how to prove these theorems one after another. We have already proved in my previous session the theorem part one with rigorous math, as well as by applying the duality principle. So let us proceed with the second one. In the second one, you are going to show that complementary element of a particular element is also very unique. So how to prove write this? So how to do this? I'm going to do part two. Okay. Now in part two, let A1 complement and A2 complement. They are both the complements of A. I'm not writing in details. Probably you are understanding. Both A1 complement, A2 complement, they are both the complements of A. Then what will happen? If it is so, then by the property Huntington's postulate, A plus A1 complement, that will give you 1. A into A1 complement will give you 0. A plus A2 complement will give you 1. A into A2 complement will give you 0. Now, if I start with A1 complement, you know that by the property of the, by one of the properties of stated in Huntington's postulate, we can write it as A1 complement into 1. No problem. Now, this 1 can be written again as A plus A2 complement. Why? Because you have assumed it. Now, it is the what? It is the distribution of multiplication over the addition. So we can write it as A1 complement into A plus A1 complement into A2 complement by the distributive law. By the distributive law, isn't it? The typical distributive law. And you know that A into A1 complement, by your assumption, this is 0. Okay, no problem. So we get A1 complement into A2. Okay, and A1 complement into A2. If this is the, we know that A1 complement into A, this becomes what? A1 complement into A, this becomes, just a minute. A1 complement into A, this will become 0, and since A1 complement and this particular result will give you A1 complement into A2. So A1 complement is becoming A1 complement into A2. Okay, and this can be written as A1 complement into A2 complement. This can be written as A1 complement into A2 complement, because why this is so? I have done, okay, I have missed some point. That's why I was missing this. A1 complement into A, and this should be A1 complement into A2 complement. Sorry, this should be A1 complement into A2 complement. Okay, now it is all right. So this line is extra. It is not required. So we get A1 complement into A2 complement. Okay. Why? Because 0 is the identity element. So we are actually getting A1 complement, which is written as A1 complement into A2 complement. Similarly, we can show that A2 complement will be same as A2 complement A2 complement into A1 complement. You try to do it by yourself, you will find this is also happening. Now, this A1 complement, if I write it as A1 complement into A2 complement, And this by commutative law, this is what? This is equal to A2 complement into A1 complement. Why? Because of the commutative law. And this A2 complement into A1 complement is again A2 complement. So you see, you started with A1 complement, you got, which is equal to A2 complement. So these two complements are actually same. And we assume that both of these A1C and A2C were the complementary element of A, but they are same. So this complementary element of A is actually a unique element, which proves the result. Just follow the logic that I have done over here. Actually, here I got a bit puzzled in this particular place previously because of the calculation mistake which I did. I missed this C from the picture, but I was actually not able to connect the things. So now this particular error has been taken care of. So this is the thing which we have in front of you. Probably you have taken the screenshot. I hope so, and I'm going to proceed further. Let us now come to the next part. Okay, so I have to show that a complement of a complement is equal to A. So how can I do this? I'm writing over here. So we can, for this number 3, we can write that for each A belonging to capital B. So this is belongs to, just a minute. For A belonging to capital B, there exists a unique element. There exists a unique element, A complement belongs to B, such that A into A complement equal to 0. By definition, you know, and A plus A complement equals to 1. Okay. Hence, A complement plus A will be equal to 1. Why? Because of the commutative law. And A complement into A, that will also be equal to 1. Sorry, that will also be equal to 0. Why? Because of the commutative law. Okay, so I have applied commutative law over here. These imply that A is the complement of A complement, and so A complement of complement equals to A. Very simple proof, quite logical. This is called the, actually this is called the logical argument, and that is called the, actually are the parts of laws of thought that Boole discussed. So part 3 is proved. Okay, now let us come to part 4. I'm writing over here. Later I will erase the what I have written. So let me write it with a different color so that you can distinguish between the two. Here we are actually supposed to show that 0, the complement of 0 is 1 and complement of 1 is 0. Okay, so I'm going to prove this part. Proof. Now we know that for every A belonging to B, we have A dot 1 is equal to A and 0 plus A equal to A. Now replacing A by 0 and 1, we get, respectively we get, if I replace A by 0 here, we get 0 into 1 equal to 0. If I replace A by 1 over here, we get 0 plus 1 equal to 1. And this shows, this simple argument shows that 0 is the complement, 0 complement is 1 and 0 is the complement of 1. So very easily, by taking the values 0 and 1 for A, we have shown the property 4. Let us now come to idempotent property. How to show this idempotent property? I am erasing this portion. Okay. So, so we have for this particular case 5, we can write it as, we start with A plus A. Here, although I have written A plus A, but with your permission, I am denoting plus by simple plus, because otherwise it takes time for me to think. We are not familiar with this kind of symbol, isn't it? So we are familiar with this plus. So we are just renaming it in this manner. So A plus A, let's start with the left hand side. We can write A plus A simply as A plus A into 1, isn't it? And this 1 can be written as A plus A complement by the property, by the axioms. Now, carefully observe. If I write this part as A plus A into A complement, I think you do not have any trouble, because this is the distribution of plus over dot. You can come back to this. Okay, so you just try to look at it carefully, that I have used the distributive property over here, and A complement is 0, you know, and therefore A plus 0 equal to A. So we have proved that A plus A equal to A. So this thing is proved. I am leaving the proof of the second part, that is A cross A equal to A, for you. You try to prove this. So it is your homework. Try to prove this property. Proof. Okay? With similar argument, similar type of argument, not similar argument, similar type of argument. Now, next we can, I'm coming to the problem number 6 of this particular theorem. In problem number 6, we are going to show that A plus 1 equal to A. Okay, how to do it? A plus 1 can be written as A plus 1 into 1, and by commutativity property, this can be written as 1 into A plus 1. This 1 can be written as A plus A complement, and this is A plus 1. And this again, by the distributive property, we can write it as A plus A complement into 1. Just look at it. And this A complement into 1 is your A complement, and this is your 1. So A plus 1 equal to 1. We have proved it very easily. I am leaving the second one for you. Prove it. And the last one, that is the absorption property. Okay, so let us try to find how to prove the absorption property. Here I'm going to show the proof, since absorption property is very important and very atypical property. Very atypical property. We have not seen such a property in our earlier cases. So I'm going to show the proof of both of these here. Okay. So proof of absorption property. Let me erase these portions. Okay. So how to prove it? First of all, let us try to prove this first one. So for the first one, we actually write it as A into A plus B. This is my left hand side, isn't it? Now, this A can be written as A plus 0. And you can write it as A plus 0 into A plus B. Again, if we apply the distributive property, we can write it as A plus 0 into B. 0 into B is your 0. So you can write it as A plus 0, A plus 0, and that is your A. So the first property is proved. What about the second one? How to prove it? This is the first one. Absorption property 1. Now I'm going to prove the absorption property 2. For 2, we have to start with we have to show this element, isn't it? Uh, the second one is very simple. You don't have to, again, you don't have to prove it by any uh, uh, in details. You don't have to show it. Why? Because here also I don't have to write it. The second part, rather I must write it in this manner. The second part of the absorption property, the second part of the absorption property directly follows from the duality principle. Directly follows from the duality principle. Think. When I'll share the note with you, I have already discussed what duality principle is in the previous session. So here also you can apply the duality principle to prove the second part. It will directly be directly derived. You don't have to do any calculation. So in this manner, we can prove all these theorems, and you see that in theorem 2, another set of theorem I have actually written over here, but I'm not going to show the proof of this second theorem because I think if I do so, now you will lose your interest, because otherwise the thing which I'm doing over here, it's a very abstract kind of thing. So I have to think of your situation also. So I'm leaving this particular theorem for you to prove by yourself. So to just see the theorem, statement of the theorem. Statement of this theorem is talking about the cancellation laws, the type of cancellation laws we discussed in the study of group theory and ring theory. Associative laws is actually coming over here. Okay, so it was not a part of definition. Associative laws are coming here in part of in a theorem. It is not coming in a definition. And several other properties have been mentioned. These properties are named as De Morgan's laws. De Morgan's laws, there are two De Morgan's laws in case of set theory, but here you see that De Morgan's laws have different forms. Some forms which you can connect to set theory, some forms are not, which you cannot connect to set theories. Okay, so you have to remember these results, because in the examination you are going to get this sort of examples. Say, if I consider the first example, you see, for instance, let us consider a plus b to be okay. I'm here. I've written that we are considering, in place of plus, we are considering this simple plus. In place of cross, we are considering simple dot. Then in Boolean algebra B, for any a b belonging to b, prove the following result. We are supposed to prove this result. Say, this result is not a theorem, but we can take the help of the definition and theorem discussed so far to prove this type of results. Okay, so this sort of questions you may encounter in the examination. So I'm going to let me try to solve one such problem. So I'm going to prove this one, okay, for you. So I'm going to do the part 1 of exercise 2. We will start with, okay, LHS. In LHS, we are writing a plus a complement into b. Okay. Now you have to memorize all the definition, all the theorems, properties that have been mentioned above to proceed with this. First of all, here I can take the help of the absorption law. How? A can be written as a plus ab, because you know this is the absorption law. So I am writing, in place of a, I am writing a plus ab, and a complement b, here I am writing it, keeping it as it is. So here I am writing by absorption law for your understanding. Next, what I can do, I can take the help of the associative law. So here I'm writing by associative law. Okay. Next, I can write it as A plus A complement B plus AB. But what sort of law is this? It is distributive law. Okay. Next, what I can do, I can take the help of no, this is not the distributive law I have used. This is the commutative law I have used. Sorry. A complement B plus AB. This is the commutative law. Now I am going to use the distributive law. So A plus okay, I'm just seeing whether if I commute the thing in this manner, whether it will be working. What I need to show whether it will come or not. Let me just think a little bit. So I'm writing A plus AB plus A complement B. Now I can use another commutative law. This commutative law with respect to addition, I think will not work out over here. So I can use the commutative law with respect to multiplication. That would be much better. If I do not, my intuition is saying that that will give me the result, required result. If it is not, then I'll come back to that. So instead of commute the two things in this manner with respect to addition, what I can do, I can write these two, AB as BA and A complement B as BA complement. This is also commutative law. This is also commutative law. Okay, then this is equal to A plus. Now if I run the distributive law, we can write it as B. Yeah, now it is coming. We can take the distributive law of multiplication over addition. Now this is the distributive law. Yeah. And A plus A complement is equal to what? It is 1, you know. A plus A complement is 1. This is the complementation law. And B into 1 is equal to B. Why? Because 1 is the multiplicative identity. So what I have shown over here, and this is right hand side, what I've shown over here, what I tried to show over here is that how to use different properties, different axioms of this Boolean algebra and different theorems and properties to prove certain results. I'm leaving the other examples for you to prove by yourself. It may take some time because I know that it is not like that after seeing the question instantly that will come to your mind that what sort of question, what sort of properties you are going to use over here. A little bit of practice and little bit of calculation mistakes will try to equip you in a better way to deal with this kind of situation. Even we the teachers also sometimes become derailed from what we need to show, and then we have to think, because at the end of the day we are doing the abstract algebra, isn't it? So it is always subjected to errors. So to err is human. You shouldn't be afraid of this. It happens with all of us. And here we have this particular thing which is called two-element Boolean algebra. What is happening over here in this two-element algebra? In this two-element algebra is what is happening is that, just a minute, instead of considering infinite set, we are considering actually a finite set with two elements only, 0 and 1. And the Boolean sum Boolean product, Boolean complement of this particular on the defined on this particular two element set is defined as follows. A very atypical of this is this one, this operation. 1 plus 1 is not 0, it is 1 plus 1 is 1. Remember, this is how the operation has been defined. You don't ask me why it is so. It has been defined by seeing some characteristics of the practical physical situation. The things have been defined in this type of manner. If you ask me why this has been taken into consideration, then I have to go back to the history of mathematics to search for. And 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. Rest is okay, no problem. This is very atypical. Multiplication is done in the following manner, complementation done is in the following manner. This, and if you in very well and easily you can show that if I consider all the elements pointwise from this set with respect to the given operations, they will satisfy all the axioms of the Boolean algebra. And then you can very well show that, yeah, this two element set with respect to these three operation is actually a Boolean algebra. And it is, since in the set there are two elements, it is called two element Boolean algebra. What is important is its practical application, which is you can find in the switching circuit. You know that an electrical switch is a mechanical device, isn't it? And which is attached to a point, as it is shown over here. And we want the current to flow from here to here in this part. If this is point A and this is point B, and these are the two switches X and Y, and you know very well that this is a series circuit. Now current will flow from this particular point to that particular point only if the two keys are closed, or the circuit is closed, or the switches are on. Switches on, circuit closed, they are similar. Switches off, circuit open, they are similar. Equivalent statement. Now you know, if I look at the picture, what are the different states of these two things? The different states are X can be open, Y can be open, both. X closed, Y closed, both. X open, Y closed, Y open, X closed. If I write it in a table form, we will get the following. So X open, X closed, Y closed, output is 1, means there will be some sort of current flow. X closed, Y open, Y closed, X open, Y closed, no current. Both open, no current. If I try to figure it out carefully, we'll see that this particular thing, operation that has been shown over here in this switching circuit operation is actually equivalent to the table 2, that is multiplicative two element Boolean algebra. If I consider the parallel circuit, you will get a similar table like this, where when state of X is both the switches are open, there is a current flow. If this switch is open and this is closed, current will flow from this through this path. If the reverse, current will flow through this path, and if both of them are open, there will be no current flow. This, if I look into this particular chart in detail, you will find that this corresponds to the additive operation of two element Boolean algebra. So here I actually wanted to show you that this circuit design, electrical engineering, or this chip design, in which is embedded on the circuit which is embedded on the chip, and the chip, the circuit is designed with respect to the algorithm written, and it is embedded in the chip. This about the embedding you study in electronics engineering. You write the algorithm, you design the circuit with respect to that, and you embed this particular circuit inside the chip. You put the chip inside the computer, and the computer runs. This is the main funda which happens. So every engineering related to every engineering, you cannot say that, yeah, I'm actually computer scientist, I don't know, I don't have to know about electronics. Electronics engineers cannot say that, shouldn't say that we are electronics engineers, we don't have to be bothered about this computer algorithms. don't you are the specialized in you are specialized in computer algorithms. Electronics engineers are specialized in embedding theory. If you want to talk among yourselves, so there must be a common medium, common source, and that common source is the basic knowledge of both the engineers in both the fields. Some basic knowledge must be there. So this two element, I wanted to show that in switching circuit problem, this two element Boolean algebra play a very important role. Now, since the percentage of students attending today's class is very poor, and frankly speaking, I have not prepared my note, I have not prepared my presentation, I have not typed my presentation any further. I had typed up to this, and here I started typing this definition, as you can see. Let me show you, otherwise you will think that I'm just bluffing. I discussed about, wrote about Boolean variable, then Boolean expression, and then up to this. So since my typing is not yet complete, then tomorrow I'm going to continue on these topics. Okay, so I'm going to stop over here at this moment, and I'm considering this poor attendance. I don't know why this poor attendance. Okay, let me stop the recording. I do not. I'm stopping my class over here.